Hello, Dr. Tushka and fellow classmates from Math 143 spring 2025. Today for my visual demonstration, I will explain the approximation of pi, how Archimedes used the methods of exhaustion to come up with a close approximation of our value of pi that we have today. I'm going to switch on over to my screen to show a demonstration of some sketches that I made, and then we're going to explain how this works on GeoGebra. So let me just switch you over here. And I will then share my screen for you all to see. Okay, so here we have some demonstrations here of some more little research that I was doing on the history of this value. The Babylonians found an approximation of 3.125, while the Egyptians found this fraction of 256 over 81, which is equivalent to 3.16. And the Old Testament and the Bible had a circular usage of 10 cubics across and 10 cubics around. A ratio from circumference to diameter is also the same for all circles. Here we have that the circumference here that we know is 2 pi times radius, and the area is pi r squared, and the volume and surface area involve pi. I'm also taking some credit from a video that was posted on our Canvas page that had more of calculations of how formulas were sort of extracted. Here, as we can see, that the area, a ratio for, let's say that's the same for all circles, is the area of the circle divided by the square of the radius. So we label these as A and A. And if you expand the radius by the scaling factor, its area is multiplied by the square of its scaling factor. So as we can see here, we have the area and the square of the radius. And if we divide these two guys right here, you see that the radius squares cancel out, and all we're left with is A, which is up here. And also same goes for here. If we divide A by 1 squared, which is here the radius, we get A back. Also, we have a more general approach of how pi r squared is found. We have here that our circle is the A, and our square is the r squared. So if we divide these two ratios by pi and do some algebraic expressions, we can find that the area is equal to pi r squared. And for approximate values of pi, using regular polygons inside and outside a circle, when we compare the perimeter with this inner hexagon with the circumference of the circle, we find that pi is greater than 3. The inner hexagon can be expanded by the scaling factor of 2 over 3 square root of 3 to form an outer hexagon tangent to the circle. So then pi is less than this 2 root 3, and then we keep repeating until we have a 96-sided polygon. And I'm going to explain more in more depth of what we are discussing. So here, geometrically, we can find that 3 is greater than pi, greater than 4. So geometry and approximation of pi was needed because there was no calculators back in the day. So we're going to show geometrically that pi lies between 3 and 4. Of course, we know that pi is a universal constant, and here's a diameter passing across a circle, passing through the center. and then we also have the circumference of the circle itself. And the ratio of these two lengths, which is circumference over diameter, is equal to 3.14. And something that I found really interesting here, even more in the readings, was that Archimedes indicated that he was publishing for the first time so that expert mathematicians could examine the proofs and judge the value, and the propositions selected mentioned were included. This one is the surface of a sphere is 4 times the area of a great circle of the sphere, or as we should say, S is equal to 4 pi r squared. And another one is if about a sphere there is circumscribed a cylinder whose height is equal to the diameter of the sphere, then the volume of the cylinder is 3/2 of the volume of the sphere, and the surface of the circumscribing cylinder, including its bases, is 3/2 the surface of the sphere. Now going back to here, this relationship of circumference over diameter, now that we have this relationship, we can pick a particular size of the circle. We want the diameter to be 1, because substituting this back into our ratio or our formula, this tells us that our circumference is exactly pi. And if we draw a shape outside with a larger perimeter and then a shape on the inside with a smaller perimeter, we will get an upper and lower bound of pi. And this is where the methods of exhaustion come into handy. Shapes must be regular polygons, and this method is the method of exhaustion that I just mentioned right now. And a regular polygon is a shape where each side is of equal length and every angle is equal. And here, if we have a triangle and we connect A and B, the shortest path is A and B. And then we also have, let's say we connect it to C, right? So we have this triangle. And let's say even we have a curve between A and B is going to be that shortest path. This is something called as the triangle law, and I was looking more into it, and it resembled similarity to Euclid's Elements from Book 1, Proposition 19. And this was some explanations made by Sandy Bultena in her explanation of this proposition, where it states in any triangle, if one of its angles is greater than another, then the side opposite of the largest angle will be larger than the two sides of the triangle. So here we're given triangle A, we're given triangle ABC. If angle ABC is greater than angle BCA and CAB, then the side AC is greater than the other two sides of the triangle. So this is some information that we're given right here, that beta is greater than alpha and beta is greater than gamma. Then B must be greater than A and B must be greater than C. So in order to prove this, a proof by contradiction was required. So if we'll prove this by contradiction. If AC is not greater than AB, then it must be less or equal to AB. If AC equals AB, then the triangle where angle ABC equals angle ACB. So here we're given that the beta is greater than alpha and beta is greater than gamma, and we're going to assume that B is equal to C, then B must be equal to gamma, but this cannot be true. As we continue here, but we have already stated that the angle ABC is greater than angle BCA, so we have a contradiction there. So now let's assume that angle B is less than C, angle C, then beta must be less than gamma. So this cannot occur right here. And this is already proven by another proposition of Euclid, which is proposition 18. I think the book was book 1, but in that case, B would be greater than C. So if line AC is less than AB, then by previous proposition, angle BCA would be greater than angle ABC. But we've already stated that angle ABC is greater than angle BCA, so we have a contradiction. Therefore, angle AC is greater than AB. So by taking the knowledge of this proposition that I mentioned here, let's say we have a circle with a diameter of 1. if we construct two line points here and connect them, we know that this angle right here that I'm highlighting is going to be greater when we connect it to this third point. So let's just say we mentioned earlier, if we use the hexagon to around this shape, a hexagon would be easier to work with. And let's say we have this square and each area is 1 and the areas of these are 1/2, right? Then we can, let's see. So let's say here we have the areas of the circle itself, excuse me, is a slightly larger distance between the 2 points, as I mentioned before. So applying this to every corner of the shape or the polygon we draw on the outside and the inside of our circle, we see that one of the inside must have a perimeter less than the circumference of our circle. And the shape on the outside must have a perimeter larger than the circumference of our circle. And so all that's left is what shapes to draw to get a lower bound of 3 that we are looking for and the upper bound of 4. So we have an upper bound of 4. Here we have 1, 2, 3, 4. And these lines have to be equal to 1. So the perimeter is 4. So now we must pick a shape with a larger perimeter. So we've tried a square, which kind of gets us where we want to. A pentagon would be more difficult to work with. It's 8-sided. But what about a hexagon? And these triangles, we have to also keep in mind that all these triangles that are formed are equilateral triangles. So here, as I mentioned before, we have them set up to 1/2. So if we multiply this by 6 triangles by 1/2, we get 3, which can be within our range. So here's a more detailed version of the method of exhaustion.
It's good to mention is the circumference of a circle lies between the perimeters of inscribed and the circumcised regular polygon end sides, and as n increases, the deviation of the circumference from the two parameters becomes smaller. So in calculating suitable approximations for pi, Archimedes circumscribed regular polygons of 6, 12, and 48, 96 sides of pentagons, right? So one thing that I'm
gonna share with all of you right now is, let's choose a different color. If PN and PN represent the parameters of the inscribed and circumscribed regular polygons of n sides, and C the circumference of the circle, it follows here that, let's say, P6 is less than P12, which is less than P24, which is less than P48, which is less than P96, which is then less than equal to Pn, less than the circumference. And you know, obviously this keeps going to Pn less than P96. Let's say P48, P24, P12, and P6. So this is based on the definition of our sequences. This would be considered a monotonic sequence that we are given. And with this given information, Archimedes was able to, you know, find a suitable approximation for pi. And what I'm going to do now is I'm going to show you all on GeoGebra how exactly we can visualize this for others to understand what is occurring here. So let me switch you over all to my other screen, my laptop screen.
So here, I believe everybody can see this right here. This was also an exploration that we did with part of our homework. If everyone wants to reference back, it's homework 3 of um, working with these different types of n values here. So for n equals 3, this creates a three-sided triangle with a perimeter of 10.392. Thus, we're finding an approximation for 2 pi, which lies between 5.196 and 10.392. Um, Archimedes found methods to find distance around the circle that were equal to the diameter, which was the circle that was inside the shape. In this case, n equals 3 forms a triangle. Each side of the triangle has length of 3. Um, and here the total perimeter is 10.392. And the inside shape is a triangle, which is a shape with a more smaller perimeter. So now let's check out n equals 6. Um, and as we see here, now we're working with a six-sided pentagon. And the circle is still obviously 2 pi. We also have a six-sided pentagon with the shape getting to an approximation of 2 pi, as 6 is now less than 2 pi, and that 2 pi is less than 6.928. The red pentagon with the perimeter here is 6.928 and makes about 6 equilateral triangles. So now let's try with a bigger number. Let's try with 12. So let's get here. Here we get a closer approximation for 2 pi. We have a now as 12-sided pentagon with a perimeter of 6.212 and the red pentagon with a perimeter of 6.212, as I just mentioned. As the value of n increases, the approximation of 2 pi gets closer. So we have an equilateral red triangle to approximate to 2 pi. So this is more a visual way of how the values keep getting closer and closer to 2 pi as we increase the ends, those equilateral triangles, as I just mentioned earlier. And that's a demonstration for pi approximation. I also want to, with the time that we have here, work on a problem from our homework uh, that I found really interesting based around these same concepts. So let me switch you all back to my other screen here.
Okay, so we are back. Um, so let me just share with all of you my screen. Uh, okay, so this was the question we can work on just to show really quickly. We're just gonna try the first part, which was I believe S of 12. So let me just bring this closer to my screen. Here we have S12 equals 2 minus root 3. And here we have the more general formula that S of 2n equals root 2 minus 4 minus Sn squared. So to get to 12, we know that we can multiply the n by 6. So here we have S12 equals 2 minus 4 minus S6 squared. And we know here from the information given that this is equal to 1. So we can rewrite this again as 2 minus 4 minus 1, which gives us 2 minus root 3 is equal to S12. And that's just what the value would be for that specific regular polygon. And in order to do the rest, you would do like a more similar process. For instance, for S sub 24, you can multiply this by 12, right here. And we already have information based on 12, so we would just have to plug it in somewhere within this expression. And that was an interesting problem that I found that I wanted to share with everyone here watching. And yes, that is basically it for that problem. So let's switch back over to my different screen here.
And actually, that concludes our visual demonstration for the approximation of pi, of how it was that value was approximated by, specifically with Archimedes and his use of methods of exhaustion. Thank you for watching, and